In this question, we want to evaluate a logarithm without the use of a calculator. The logarithm that we want to evaluate is log base 5 of 125. So the strategy that I use for evaluating these logarithms without a calculator involves converting them to an exponential instead of a logarithm, which I'm much more comfortable simplifying. So my strategy is that I have this log expression and I'm not sure what it equals. So I'm going to let it equal p, and I'll explain in a little while why I chose the letter p as the variable. And when I have it written this way, what I have is a logarithmic equation. And what you see in this purple bubble here is something that I pulled from the definition of a logarithm. The definition of a logarithm is based on it being the inverse of an exponential. So every logarithm can be written as an exponential if we follow this pattern. So what you'll notice is that with inverses, the x's and y's get switched. And so I'm substituting x into the log, but for an exponential, it's in the position that y is usually in. So that x and y positions get switched. And then here I have the y, which is usually which x would usually be in that position, and that is what the log is equal to. And so we're going to pay attention to this relationship between the log and the exponential. I'm going to pay attention to the position of all of these symbols so that we can see how to translate our equation into an exponential equation. So let's go symbol by symbol, and I want you to notice that we have the base of the log being the same as the base of the exponential. The log equals y, and y is the exponent. So that log is equal to the exponent, and then the exponential expression equals x, and that is what is inside the log. So when we convert our equation to an exponential, we need to follow the same pattern. So we notice that the base of the log is 5, and that will be the base of our exponential. The log is going to equal the exponent. And so for our exponent, we're going to use p. And hopefully it makes sense why I chose the letter p, because sometimes exponents are called powers as well. So then we have this exponential expression will equal what we have inside the logarithm. So that's going to give us the statement 5 to the p equals 125. So this equation that we have in exponential form is equivalent to the equation that we have in logarithmic form. And now that it's written in exponential form, it's much easier for me to figure out what that value of p is. So I've got 5 raised to a power equal to 125, and I know that 5 to the first is 5, 5 to the second, I wrote that wrong, 5 to the second power will be 25, and 5 to the third power is 125. So 5 cubed is 125, and now I know the value of p. And p is what I said that this log equals. So now I know that log base 5 of 125 equals 3. solve the exponential equation using the method of relating the bases by first rewriting the equation in the form e to the u equals e to the v. So this method of relating the bases starts with having you write the equation so that the bases are the same on each side. And once you have it written this way, you can say that the exponents must be equal to each other. So this allows you to solve a simpler equation than the original exponential equation. The equation that we're working with is 1 over e to the 5x equals square root of e over e to the 2 minus x. So I'm going to start by trying to make bases the same on both sides. You can see the expressions that I have base e, and so that's what base I'll use on each side is base e. And as I do this, I'm going to be using some properties of exponents. And as I use the properties, I'll write which properties I'm using on the right side. So one of the properties I'm going to use on the left-hand side involves negative exponents. And this property with negative exponents says that if you have 1 over a to the n, that you're able to write this with a negative exponent as a to the negative n. And it goes back to having negative exponents means reciprocal of the base. So on the left-hand side, I'm going to be able to write the expression 1 over e to the 5x as e to the negative 5x using that property of negative exponents. Then on the right-hand side, I have a radical. And radicals can be written as powers. So in general, if you have the nth root of some value x, you can write that as x to the 1 over n power. Every radical can be written as a power. Now we're dealing with the square root of e, and it doesn't have an index listed on the radical. And when you have no index listed, we know that that's the square root and the index is 2. So I'm going to be able to write the square root of e as e to the 1/2 power. I'm going to copy the denominator down. And the next property of exponents that we're going to use involves the fraction that you see on the right. And we call this property that we're going to use the quotient rule for exponents. And the quotient rule for exponents says that if you have a base to a power divided by that same base to a power, then you can keep that base and subtract the exponents. So b to the m over b to the n is b to the m minus n. And that's what I have on the right-hand side of this equation. We have the bases that are the same, and the expressions are being divided. So we'll use that quotient rule for exponents and subtract the exponents. I'm going to copy down the left, and then on the right, we have that base of e, and we'll do 1/2 minus 2 minus x. The bases are the same on each side of the equation now. And now that those bases are the same, I can say that the exponents must be equal to each other. So the exponent that we see on the left must equal the exponent that we see on the right. So this is using the method of relating the bases, or other sources might call this the one-to-one property of exponents. So we can say that negative 5x is equal to 1/2 minus 2 minus x. And this gives me a much simpler equation to solve now that those exponential expressions are gone. So I'll use the distributive property with this negative. Negative 5x equals 1/2 minus 2 plus x. And it'll be a little easier to solve this problem if I didn't have a fraction. So I'm going to use the clearing fractions method and multiply 2 times every term. That would give me 10x equals 1 minus 4 plus 2x. Let me copy the equation down up here so I have a little bit more space to work. On the right-hand side, I have some like terms. 1 minus 4 is negative 3. And I'd like to collect the x's, so I'll subtract 2x on both sides. That gives negative 12x equals 3. And then I can solve for x by dividing by negative 12 on each side. That gives x equals negative 1/4. So x equals negative 1/4 is the solution to this equation. So I have a correction that I need to make here. I'm going to highlight the mistake that I made. So right here I have x equals negative 3, and when I carried it down, I didn't carry the negative. So I'm going to correct this to be a negative 3. And negative 3 divided by negative 12 would be a positive 1/4. So the solution is x equals 1/4. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. So with the method of relating the bases, we start by writing the equation as b to the u equals b to the v, and then we can use the one-to-one property of exponents or exponential functions to say that the exponent on the left must equal the exponent on the right. So this allows us to simplify the equation and continue solving. The equation we'd like to use this property on is 5 to the x squared over 25 to the x equals 125. So we want to start by making the bases the same, and I am going to take a closer look at the bases that I have. I have a base of 5, a base of 25, and a base of 125. Notice that these all end in 5, and these also happen to be powers of 5. 5 is 5 to the first power, 25 is 5 to the second power, and 125 is 5 to the third power. So it seems like 5 would be a good base to transition to. So I'm going to rewrite all of the bases with base 5. That would give 5 to the x squared. 25 is 5 squared. And we need to carry down that x, the exponent of x. And I'll write 125 as 5 to the third power. I'm going to use a property of exponents to simplify. And the property that I'm going to use is called the power rule for exponents. And the power rule for exponents deals with the situation where you have a base to a power, and then that whole expression is raised to a power. And when you have this situation, you simplify by multiplying the powers together. So b to the m to the n is b to the m times n. So to simplify what I have highlighted in yellow there, we would have 5 to the 2x, because 2 times x can be written as 2x. The others I'll copy down. I'm going to use another property of exponents to simplify the left-hand side of this equation. We're going to use a property called the quotient rule for exponents. And the quotient rule deals with this situation where you have b, a base to a power, divided by that same base to a power. The base b to the m over b to the n. And when you have this situation when you're dividing exponential expressions with the same base, you're going to simplify by subtracting the exponents. That's b to the m minus n. So let me draw an arrow and we'll continue simplifying up here. On the left-hand side, I would have 5 to the x squared minus 2x, applying that quotient rule for exponents. I'm going to copy down the right-hand side. So I'm finally at the point that was described in the directions of this problem, where we have the base being the same on both sides. So I'm able to simplify this equation by saying that the exponents must be equal to each other. The bases are the same, so the exponent on the left must equal the exponent on the right. So that gives x squared minus 2x equals 3. This is a quadratic equation, and I'll move all the terms to the same side. And I'll solve this quadratic by factoring, but you're welcome to use a different method, like the quadratic formula if you prefer. So x times x is x squared. 3 times 1 is 3, and I need to create a middle term of negative 2. And I would do that by having a negative 3 and a positive 1. Once I get it factored, I'm going to set each factor equal to 0 and solve. That gives x equals 3 and x equals negative 1. So these are the solutions to the exponential equation, x equals 3 and negative 1. Evaluate the expression without the use of a calculator. The expression we're working with is log of 1 over 10 million. So the strategy that we're going to use to simplify this logarithmic expression is to write it as an equation to start with. So I'm going to say I don't know what this expression equals. Let's say it equals p. I'm using p for power or exponent. And once I write it as an equation, I'm using this, which I pulled from the definition of a logarithm. And the logarithm is defined in terms of its inverse, an exponential. So this gives us a way of coming up with an equivalent equation that is in exponential form. So here we have a log equation and the equivalent exponential equation. So the base of the log is the base of the exponential. The log equals y, which is the exponent of the exponential. And the exponential equals x, which is the value that is inside the log. So this pattern allows us to convert back and forth between log equations and exponential equations. So let's do that for our example. Log of 1 over 10 million equals p. So the first thing that's a little bit strange here is that in our definition, we have in a smaller font, lower, we call that a subscript, this value of b, and in the example that we have, there is no number with a smaller font in that subscript position. And when there is no number in that position, we assume a base of 10. It's called a common log. It is the common base for us to use. So this equation would be the same as log base 10 of 1 over 10 million equals p. So we assume that that base is 10 when we don't have one listed. And now that we know the base, we're going to use that as the base of our exponential. So we're going to use 10 as the base. Then our logarithm equals p, and that is in the position of the exponent for our exponential. So we're going to use p as the exponent. Then our exponential equation is going to equal what is inside of the logarithm, substituted inside of the logarithm. So that's going to be 1 over 10 million. So we've rewritten this we've rewritten the logarithmic equation as an exponential equation. So now when it's in exponential form, we're going to try to figure out what that value of p is. So as we look at this, we have 10 to a power equals 1 over 10 million. Let's write it without all the highlighting. 10 to a power equals 1 over 10 million. There, I got my comma in the wrong spot there. So we want to figure out what that value of the exponent is. And one strategy that we could use is one that we've seen before, relating the bases. If we can write these both with a base of 10, we'll be able to figure out what that exponent is. So 10 million, you can see it has all those zeros. I can write that as a power of 10. So 1, 2, 3, 4, 5, 6, 7. So that's 10 to the 7th power. And then I can move this to the numerator using one of the properties of negative exponents. That's 10 to a power equals 10 to the negative 7. And now that I have these bases being the same, I can see that the power is negative 7. So p is negative 7. And this log expression, log of 1 over 10 million, is equal to negative 7. Sketch the logarithmic function, label 3 points that lie on the graph, and determine the domain and the equation of any vertical asymptotes. The equation that we want to graph is h of x equals log base 4 of x. This is a logarithmic function, and as I look at this logarithmic function, I don't see any transformations to it, so this is just one of the basic logarithmic functions. But I'd like to write this, instead of h of x equals log base 4 of x, I'm going to write it as y equals log base 4 of x. And the reason I'm doing that is because I'd like to write this in exponential form instead of logarithmic form. It's much easier for me to find ordered pairs in exponential form than in logarithmic form. So if I write this in exponential form, it would be a base of 4 to the power of y equals x. So now I'm going to find some ordered pairs. Notice it says to label 3 points. So we want to find at least 3 points, but I like to find 5 because I get a much better defined graph when I have 5 points. So usually when I'm making a chart like this of x's and y's, I would choose x's and find y's. But we only do that when our equation is written in y equals form. I've just rewritten the equation so that it's in x equals form. So this time I'm going to choose y values and find the x's. I'm going to choose just a standard set of y's, -2, -1, 0, 1, and 2. We'll substitute these in to the equation 4 to the y. I'm going to start down here where the values are a little bit easier to simplify. 4 to the first power will be 4. 4 to the second power will be 16. 4 to the 0 is 1. 4 to the -1 is 1/4. And the reason I get 1/4 is because I'll use that negative in the exponent to tell me to find the reciprocal of the base. And 4 to the -2 will be 1/4 squared, which is 1/16. This gives me a set of ordered pairs. 1/16 -2, 1/4 -1, 1 0, 4 1, 16 2. I'm going to plot these ordered pairs. 1/16 and -2 would be about here. 1/4 and -1 would be about here. 1 0 would be here. 4 1 and 16 2. So 12, 13, 14, 15, 16 is a little off my grid, but we can still see it about right here. These 5 points connect very smoothly, and you can see how the pattern would continue on the right and on the left. Our graph would go down to -infinity. This logarithmic function will have a vertical asymptote that sits right on top of the y-axis. The vertical asymptote being the vertical line x equals 0. And you'll also notice that the graph is only showing up to the right of that y-axis. Logarithmic functions can only accept positive values inside of the log. And so we have a domain of 0 to infinity for this logarithmic function. So we have a graph where we've labeled 3 points, we've determined the domain, and we've determined the vertical asymptote for this log function. Find the domain of the logarithmic function. The function we're working with is f of x equals log base 2 of -4 minus 7x. Now, logarithmic functions are defined only for positive values, which means that the expression inside of this logarithm must be positive in order for the log to be defined. So I can find the specific domain for this logarithmic function by taking the expression inside of the logarithm, -4 minus 7x, and we're going to create an inequality where -4 minus 7x is greater than 0. When I solve this inequality, it'll tell me the domain of the function. So I'll add 5 to, not 5, I'll add 4 to both sides. That gives negative 7x is greater than 4. I'll divide by negative 7 on both sides, and when you divide an inequality by a negative, you need to reverse the inequality symbol so that it maintains its truth value. So on the left we have x, and on the right we have negative 4/7. So we have x is less than negative 4/7. This is going to be the domain of our logarithmic function. We want to write that domain in interval notation. So I'm going to mark negative 4/7 on the number line, and we would mark that with an open circle because we don't want to include it in the domain. Negative 4/7 will cause the expression inside the log to be 0, and log of 0 is undefined. And we're going to shade the values to the left because these are the values that are less than negative 4/7. And the domain will start using that shaded region, start at negative infinity, and go to that value of negative 4/7. We're going to include a parenthesis next to negative 4/7 because we don't want to include that in our domain. So we have a domain of negative infinity to negative 4/7. Use the power rule to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expression. The expression we'd like to simplify is log base 2 of t to the 8th. So the directions specifically say to use the power rule, and I've brought here the power rule for logarithms for us to take a look at. This power rule deals with a situation where we have an exponential expression within our logarithm. We have log base b of m to the power p. Now the way that we can simplify that using the power rule is to move that power into the position of the coefficient of our logarithm. And so that's what we're going to do with our example here. We do have an exponential expression, t to the 8th, inside of our log, and we're going to be able to take that exponent of 8 and move it into the coefficient of the logarithm, and that would be applying the power rule. So that would give 8 times log base 2 of t. Use the properties of logarithms to rewrite the expression as a single logarithm. Whenever possible, evaluate the logarithmic expressions. In this example, we want to simplify log of 50 plus log of 200. So we're going to use the properties to rewrite this log as a single logarithm. I like to call these properties the expanding and condensing properties. And when we want to write them as a single logarithm, we're trying to condense to a single logarithm. So in our example, we have a plus, and I'm going to look through these rules and notice that the product rule has a plus in the expression here. So when we're adding two logs with the same base, we're going to be able to combine that or condense that to a single logarithm with multiplication, and that's why this is called the product rule. Now, when I look at the logarithms we want to make sure that before condensing them, they have the same base. I have log of 50 and log of 200, and the base is not specified. When the base is not specified, we assume that it has a base of 10. So this actually means log base 10 of 50 plus log base 10 of 200. Now that we are sure that we have the same base, we're going to condense these using that product rule. We condense to a single logarithm of base 10, and we condense with multiplication. So that's 50 times 200. That's log base 10 of 10,000. Notice in the directions of this problem, it says, whenever possible, evaluate the logarithmic expression. So anytime you have log of a number, you should try to simplify it further. So in this example, I have log base 10 of 10,000, and I can say I'm not sure what this equals, and I can rewrite this as an exponential equation. As an exponential equation, it would be 10 to a power equals 10,000. 10 to what power is 10,000? 10 to the fifth power is 10,000. And so that's telling me that this power, p, is 5. So I now know that log base 10 of 10,000 is 5. And we have simplified our original log expression, log of 50 plus log of 200, to be 5. Use the properties of logarithms and the logarithm property of equality to solve the logarithmic equation. The equation we want to solve is natural log of 6 plus natural log x equals natural log 8 plus natural log of 4x minus 2. So first it says that we're going to use properties of logarithms as well as the property of equality to solve this equation. So first I want to take a look at the property that we're going to be using to solve, and that's the property of equality right here. Some sources call it the one-to-one property of logarithms. So what this property says is that if you have log base b of u equals log base b of v, so that means you have the log with the same base on both sides, then what's inside the log on the left must equal what's inside the log on the right. So it allows you to simplify your equation to no longer having logarithms in it. Well, as we look at this, it requires us to have a single log on the left and a single log on the right. And as we examine our equation, we don't have a single log on the left and we don't have a single log on the right. And that's where these other properties of logarithms come into play. We want to use the properties that we see down here, the product rule, the quotient rule, and the power rule, in order to condense our equation to having a single log on one side, on each side, single log on each side. And so on the left, I can see I am adding two logs together. I'm going to be using this property of the product rule in order to condense. So when you have the sum of logs, you're going to condense with the product rule. I have the sum of logs on the left and the sum of the logs on the right. So I'll be using that product rule on both sides. But just double check before you do that to make sure that your logs have the same base, because you're not able to condense to a single logarithm unless you have the same base. In this example, we have ln, which stands for natural log, and that means that we have log base e. So I'm going to rewrite this equation in its equivalent form. So this equation actually means log base e of 6 plus log base e of x equals log base e of 8 plus log base e of 4x minus 2. I got a little sloppy at the end there. Let's rewrite that. Log base e of 4x minus 2. So we do have the same base on every one of our logs, so we are able to condense and we are able to use the property of equality. So on the left-hand side, I'll condense my logarithms using that product rule to become log base e of 6x. I multiplied 6 and x to condense. And on the right, I have log base e of 8 times 4x minus 2. And now you can see I have a log base e on the left and a log base e on the right. So I can apply the property of equality, and what's inside the log on the left must equal what's inside the log on the right. This gives me a linear equation, which I'll solve. I'll use the distributive property on the right to get 32x minus 16. I want to get the x's onto the same side, so I'll subtract 32x on both sides. That leaves a negative 16x on the right, and on the left I have six. 26. Negative 26x. And then I'll get x by itself by dividing by negative 26 on both sides. And that leaves me with x equals, and I can reduce this fraction. They're both even. 2 goes into 16 8 times. 2 goes into 26 13 times. So we have x equals 8 over 13. Now when you're solving logarithmic equations, you do need to check your solution to make sure that it's in the domain of the original logarithm. So we're going to check our solution of x equals 8 over 13. In the equation we have natural log 6 plus natural log of 8 over 13 equals natural log 8 plus natural log of 4 times 8 over 13 minus 2. So I can see that 6 is positive, 8 over 13 is positive, 8 is positive, and I just need to check to see this 32 over 13 minus 2 if that's positive, which it is. 32 over 13 is more than 2, so this will also be positive. So the reason why I'm checking to see if they're positive is because the log of positive numbers is defined, log of 0 is undefined, and log of negative is undefined. So if any of those expressions had a negative inside the logarithm or 0 inside the logarithm, then we would throw that solution away. We will keep this solution of 8/13 because they were all positive. Use the properties of logarithms and the logarithm property of equality to solve the logarithmic equation. The equation we want to solve is 2 log of x plus 5 equals log of 16 plus log of 4. Now we're going to use this one-to-one property of logarithms, or the way that your book calls it is the property of equality, which says if you have log with the same base on each side of your equation, then what's inside of those logs must be equal to each other. So this provides us a way for simplifying logarithmic equations to something we're a little bit more comfortable solving. We want to do that with our equation, but you can see that on the left of our equation we have a single log, and the right of our equation we have a single log. And in our example, we have a log on the left with a coefficient, and we have two logs on the right that are added to each other. So we can use some properties of logarithms that allows us to condense and simplify these expressions first. And once we rewrite it in this form, where we have a single log with the same base on each side, then we'll proceed with solving. So on the left, I need to deal with this coefficient of 2. And there's a property of logarithms called the power rule, which allows me to move that power, to move the coefficient into the power. So that would mean on the left-hand side that I would have log of x plus 5 squared. And then on the right-hand side with this plus sign, I'm going to be able to condense these logarithms with a property called the product rule. And it's called the product rule because we multiply the numbers inside of each log. So we're going to multiply 16 times 4. So that's going to give 64. So on the right-hand side, we have log of 64. So now we've written this equation with a log of the same base on each side. Take a second to see if you can remember what base is being used for these logs when we don't specify. When we don't specify, that means we have a base of 10. So this actually means log base 10 of x plus 5 squared equals log base 10 of 64. So we're able to now use that property of equality and say that x plus 5 squared equals 64. We can make an equation out of the expressions inside the logs. So now we'll continue to solve. This is a quadratic equation. I'm going to solve with the square root method. So I square root the left and square root the right. On the left, the square root and the square cancel each other out, leaving me with x plus 5. On the right, I have plus or minus 8. I'll subtract 5 on each side, giving me x equals negative 5 plus or minus 8. Negative 5 plus 8 is 3. Negative 5 minus 8 is negative 13. Now with logarithmic equations, you need to check to make sure that your values are in the domain of the original function. So let me check x equals 3 in the original equation. That's 2 log of 3 plus 5 equals log of 16 plus log of 4. And when we check, what we're checking for is to make sure that our value is in the domain of the log. And we can only take the log of positive values. So we're checking to see if this expression inside the log is positive, and 3 plus 5 is positive, and these other expressions inside the log are also positive. So we're going to keep the solution of 3. Now let's check the other solution of x equals negative 13. That would give 2 log of negative 13 plus 5 equals log of 16 plus log of 4. And you can see that this expression inside the log, negative 13 plus 5, would give you a negative value, and the log of a negative is undefined. So we're going to throw away that solution of negative 13 and keep only x equals 3 as the solution to this log equation. Thank you for checking out my videos. Have a great day.